Hi, everybody. Welcome to our webinar. My name is Dennis.Sack, Senior Vice President, Principal Engineer of Olson Engineering. And welcome to our ongoing series of webinars on non-destructive testing and geophysics. Today, we're going to be discussing the evaluation of bridge foundations or of unknown foundations. We'll be covering methods to evaluate both shallow and deep foundations, and we'll have time for questions at the end. Questions will be entered via the chat box. So with that, let's get going here. Again, we're going to be discussing the evaluation of unknown foundations. So there's 5 methods we're going to be discussing today. The most common methods are sonic echo, impulse response. This is also the method called the pile integrity test method, PIT. And the other common method is the parallel seismic method, or the PS method. We will also be talking about several other methods that are primarily used for shallow foundations, including ground penetrating radar for, again, shallow foundations and footers, impact echo, again, primarily for locating footers or evaluating footers underneath slabs, and a quick little discussion on electromagnetic borehole tool. This tool can locate steel in the ground. There are several standard references for non-destructive testing methods. These include the ACI 228.2 report, which covers non-destructive test methods for evaluation of concrete and structures, and includes the evaluation of foundations. As you can see, Chapter 3 has a summary of the various methods. Chapter 4 is on planning and performing a non-destructive testing investigation. There are also a number of ASTM standards related to the evaluation of foundations. The first is the sonic echo impulse response, has an ASTM D5882, and that one covers, again, echo testing for foundations. There's a parallel seismic ASTM standard, which is in work. It is currently in the balloting process, committee that I'm involved in, so that should be coming out not too long. Ground penetrating radar also has an ASTM standard, and the borehole electromagnetic tool has an ASTM standard. We will discuss unknown foundation limitations. The sonic echo impulse response method, primarily used for drilled shafts, auger cast piles, timber piles, concrete driven piles, and can also be used on mat foundations. It has a couple of basic limitations. The SEIR method, you have to have access to some part of the foundation itself, either the top or the upper side. Sometimes you can do this method through a pile cap. Sometimes you can do it through an actual slab. There's some limitations on those based on the geometry, the diameter of the pile, how thick the slab is, etc. There's also a limitation with the echo testing method on the length to diameter ratio. It's best on shorter, fatter foundations. For driven piles, you can often get away with higher ratios because they have very smooth sides and are very even. On drilled shafts, it's usually not quite out to the 50-to-1. For auger cast piles, you're lucky to often get 20-to-1, just because they tend to be very uneven as you go down the shaft. The parallel seismic method, again, can be used on pretty much any type of foundation. There's a whole list on the screen, as you see. The biggest limitation of the PS method is it requires a borehole adjacent to the pile. The closer that borehole is to the foundation, the better your results will be. Typically, we like that borehole to be within about 10 feet of the edge of the pile, of the foundation. You can do it. There's been some experiments doing parallel seismic with a seismic cone probe in some circumstances. There's a basic limitation of that, and that the cone probe has to be able to push down beyond the tip of the pile. And many driven piles, at least, tip out at a very hard layer that the seismic cone probe can't get past. So there are certain situations where it works all right, though. The biggest advantage of the parallel seismic method is that there is no direct access to the foundation itself required. I have done a test with parallel seismic and gotten usable results hitting a bridge deck above a column that was above a buried pile cap that was above the actual foundation that we were measuring the tip depth of. And that resulted in very usable parallel seismic data. So you don't need access to the foundation itself. We often do this hitting buildings, hitting columns, hitting pile caps, etc. Because of this, the parallel seismic method is considered to be the most effective and flexible method for unknown foundations. The other test methods, there's the ground penetrating radar, again, primarily for footer location underneath slabs, for measuring the area and depth of shallow foundations, and we've used it on mat foundations for bottom depth. There is a limitation on how deep you can see the top of a footer, depending on the soil type and how much moisture and some other factors. And there's a limitation on how deep you can see through a mat, obviously, depending on how much rebar and what antenna frequency you're using. Another method, impact echo, the IE method. Again, we primarily use this for shallow footers. We use this on slabs to locate thickened areas in the slab, to locate footers and measure how deep they are. It does require, similar to the SEIR, direct access to the top of the concrete. We have a scanning impact echo application where you can roll the impact echo transducer across a slab and very quickly locate the footers underneath it or thickened slabs. And I've got some examples later in this presentation showing just that. And finally, this borehole electromagnetic tool, it's kind of an unusual application. One of our first applications of this was an interesting project where the drawings appeared to show that the rebar mat only went halfway down the drilled shafts. And it turns out it was probably because someone was a little careless with how they made these old drawings. Regardless, we were asked to come in and verify that the rebar actually did go down all the way to the bottom of the foundations. And this electromagnetic tool worked really well for doing that. It does require a cased PVC borehole to be located very close to the foundation because, again, you have that cubed relationship between distance and signal strength. So let's get into some of the individual test methods. We're going to start with what's probably the most common method for foundation evaluation, especially existing foundations. Sonic echo impulse response. Again, that's also called low strain integrity testing, also called pile integrity testing or PIT. There's a lot of different names for it. I've even heard it called impact echo from some DOTs. But it is used for foundation tip depth and integrity. So the sonic echo and impulse response are really you can think of them as the same method, but analyzed in different ways. Sonic echo is analyzed in the time domain. So you're looking at the time of echoes coming back. Impulse response, on the other hand, is analyzed looking at the frequency of the echoes. And there are some strengths and weaknesses to each way of analyzing this data. And each one gives a little bit of a different nuance to how you can look at the data. Essentially, you're impacting the top of a deep foundation and recording the echoes from the foundation bottom and/or from defects in the foundation. Again, we've used this in auger-cast piles and mats. We've also used this method on wall-type structures, such as cutoff walls and abutments or wall piers on bridges. One thing I should point out, the echo testing method is usually not applicable to steel H-piles or steel piles of any sort. We have used it on some very short steel H-piles and gotten usable results, but that is not very common. Most of the time, the energy dissipates out of the pile too fast before it gets down to the bottom and has a chance to echo up to the top. So here's a quick diagram showing the SEIR method. Essentially, you have a hammer and a receiver, either a geophone or an accelerometer is the most common. You impact the top of your foundation. The sound wave travels to the bottom. If the foundation is sound, it echoes from the bottom, comes back up to the receiver. By estimating or measuring the velocity of the concrete, which is typically around 12,500 feet per second for most normal concrete mixes, and measuring how long this echo takes to come back to the top, you can determine how deep this tip is. Now, if your shaft has a neck or a full break, you will get echoes from that shallower intrusion or that shallower feature. A full break will echo only from the shallow depth, whereas a partial neck, you may see both echoes. And I've got some examples later again showing that. One thing interesting about the echo test method is that you can also detect bulbs, what they call a impedance increase. A bulb would be effectively a diameter increase, and it echoes with an opposite polarity from a neck. And so you can tell the difference between a bulb and a neck. Some of the basic issues you have to deal with: the top must be accessible. Top ideally should be relatively smooth. I haven't had to grind a top in a while. We can usually make it work. We have done testing from the upper sides of foundations in case you can't get to the top, but you can get to the side. That's common on, say, timber piles, where we can mount to the side of a timber pile. And as I noted, we have tested shorter steel H piles, but it's not normally recommended. It doesn't usually work very well. Basic equipment for echo testing, some sort of PC-based signal analyzer or handheld unit. Olson Engineering, Olson Instruments makes an NDE 360. There's also a tablet-based system such as our FTG1. You also need some kind of hammer, typically an impulse hammer. You need a instrumented impulse hammer to do the impulse response testing. You can get away with what we call a dumb hammer, just a regular hammer for sonic echo testing. You also need some sort of receiver, geophone or accelerometer. The most common receiver is going to be an accelerometer for that. And of course, you need some sort of software to analyze the data and pick your arrival times and calculate the depths. Here's a picture showing some of the basic equipment. This is a Freedom NDT, Freedom Data PC with a geophone. Over here is a small accelerometer. This is an instrumented 3-pound hammer. We typically use grease to stick the accelerometer and geophone down. There's other options for that as well. ND 360 can do the same test. And then the FTG, that's just it simplifies it using a tablet or a laptop as essentially the data acquisition platform. So it's just a small module accelerometer and in this case, a dumb hammer. This would be a hammer that's not instrumented. This is a photo, just really quick, showing mounting on the top. You can see this has been ground really nicely. You have a geophone here, an accelerometer here, and the testing going on and impacting the center of the foundation to generate the sound waves that go down. One thing I should point out, if you're familiar with the ASTM standard for SEIR testing, they do want, for larger diameter foundations, testing to be done at a minimum of 3 locations around the perimeter of the foundation top. For smaller foundations, a single test location is adequate. The reason we like to have 3 locations is that if there's a shallow defect, say in the top 2 or 3 feet of the foundation, you may not see it on imagine a 6-foot diameter shaft, your accelerometer is over here, your defect is in the third of the shaft over here. It takes a couple of diameters of the shaft before that wave from the impact develops into a full diameter wave. So typically you want to test at least 3 locations just so you don't miss those possible shallow defects or shallow issues on a shaft top. And the ASTM standard was written to handle that. I wanted to show you a couple of photos of a recent project showing ways that mounting and testing can be done. The most common, of course, is testing directly on the foundation top. This is the simplest, the easiest, and usually results in the best quality data. Here we have an NDE 360, an accelerometer, and a geophone, and an instrumented hammer, all ready to test on this foundation. Over here on the left, you can see we have a slab. It's maybe a pile cap, it's some sort of slab. This particular one, the foundation was large enough in diameter. Typically, your foundation diameter needs to be larger than the thickness of the slab or pile cap you're trying to test through. In fact, there's a little equation for that, but I won't go into it at the moment. But in this case, the slab or pile cap was thin enough compared to the shaft diameter that we could see very clearly the data from the foundation itself. So no saw cutting, excavation, or other extra effort was required to get good data on this particular tower foundation. We were able to test right through the slab top itself. This is another unusual application of the echo testing method. This is a buried cutoff wall. You can see the top of the wall is actually under the earth. This was excavated out for us. And this cutoff wall extends for quite a distance. And we were looking for depth and integrity of the cutoff wall at selected locations. And so they excavated some holes, and we were able to test on the top of the wall and get usable data from the bottom of the wall. We were able to measure the wall depth. And in some cases, we're able to locate some issues that may have required some additional excavation. One final photo showing some of the ways that this test method can be applied. This is testing a foundation under a pile cap. And you can see here the accelerometers are mounted on steel blocks that are then grease coupled to the side of the foundation. When you do mount to the side of a foundation, it's very, very important to squish out all the grease and really get a tight bond to the foundation side. The alternative is to use something like a 5-minute epoxy on this block, etc. The other important thing to remember when you mount on the side is the accelerometer must be vertical. We've seen people try to do this test where they stick the accelerometer on horizontally and the data isn't usable. The accelerometer has to be vertical. That's why we need a block on the side. But you can work with testing a foundation underneath a pile cap, you do the same way on a timber pile. And the analysis of SER data is based on reflections. You're getting the depth of the pile, and you can also get defects along the pile shaft length. You can use the impulse response data to determine dynamic stiffness, but we won't really talk about that too much today. That's not used too often, but it is another it's the low strain dynamic stiffness of a shaft. Good, a little bit of technical basis here. The echo you're looking for from a typical pile tip is called a free echo. In other words, when you hit at the top, your accelerometer, the pile cap moves down, and the accelerometer shows that. The echo goes to the bottom, moves down, comes back to the top, also in the downward direction, so your echo is downward. If you have a impedance increase, this would be a bulb or a bell at the bottom of the shaft or a shaft sitting on really hard bedrock, your response actually inverts. So you'll have an upward break from the bottom of the shaft. So a bulb will break upward, whereas a neck breaks downward. And that's how we tell the difference between necks and bulbs. In the impulse response method, we're measuring the change in frequency rather than the change in time. And I apparently neglected to put the equation on here, but the depth of the foundation is equal to the velocity divided by 2 times this delta F. That's the simple equation for the depth of a foundation in the impulse response method. What this slide is showing is that the mobility shifts by half of a frequency spacing when you have a bulb versus a neck. So let's see some actual data. This is real data from an accelerometer showing a shaft that's 17.7 feet deep. What I like about this one is it's showing multiple echoes. We can actually see 1, 2, 3, 4 echoes from the tip of the shaft. This is what the hammer impact looks like. It's just a half sine wave impulse. So we can analyze this data in the sonic echo mode, the time domain, and come up with about 17.7 feet. This is the equation, velocity divided by time over 2, 12,500 feet per second. I'm sorry, yeah, times 2.83 milliseconds over 2, 17.7 feet. In the impulse response, we measure the frequency spacings. This one came up with a slightly different depth because of where these peaks were picked, but you can look at the impulse response data as well. As you can see, this spacing from here to here is about even from here to here. This tells us this is a neck type or a typical bottom echo. The lower plot is your coherence. This gives a measure of data quality. Now let's go into some of the interpretation. I've got some slides showing typical shaft conditions or defect types, along with what the typical plots look like. These were plots on actual data with real shafts with verified conditions. So these are some of the situations you may run into: a normal shaft, a short shaft, a broken shaft, a shaft that's broken at very, very shallow depths, a long bulb or a diameter increase that extends for a long distance, or a short bulb. This would be a short diameter increase. A bottom bell. For those of you in Texas, that's where we seem to see most of the bells. A shaft set into a hard rock socket. And then finally, shallow necks or inclusions. Now, I should note that some of these get the same type of result because from an acoustic standpoint, they're really the same type of thing. So typical SE data from a sound shaft. You got the initial hit, you have the echo. This is a 50.6 foot shaft, really nice, clean data. From a short shaft, you have the impact, you have the echo. This was only 23 feet. Now, if you have a shaft that's broken, you may get the same, you're gonna get an echo, the same type of echo you would from a short shaft. You can't tell a short shaft from a broken shaft unless you know how deep the shaft is supposed to be. That's kind of makes sense. But it will definitely show the depth, the effective depth of your foundation. This is the data we get from a very, very shallow break, particularly with a 3-pound hammer. The 3-pound hammer is generating more low frequency energy, but there's high frequency energy riding on top of it from these very, very shallow echoes at only 5 feet. This was a shaft underneath a pile cap that had some unusual settlement. We tested the shaft, it showed only 5 feet. They dug it up, and sure enough, it was broken off, just barely underground. So this was verified to be a typical short shaft or a shallow break. Now, this is an example of how complex sonic echo data can be, and yet you can usually get there's a lot of information here. So these were newly drilled shafts that were being tested for quality assurance. We knew that the shaft was 34 feet deep. And so we found that there was indeed a clear echo at 34 feet right here. However, we had some other echoes, particularly this one. Our worry is this a defect, a partial neck? Well, we saw this, we have the initial response to the hit, and instead of going down to the zero line like it normally does, it actually broke back up. That's what a bulb would do, a diameter increase. Then it broke back down, a diameter decrease, and it didn't cross the zero line, so that tells us it's likely just going back to the original diameter. Well, sure enough, when we checked with the driller, there was indeed a sand layer from about 8 or 9 feet down to about 13 to 14 feet. And that soft sand layer was caving in while they drilled and making a long bulb. So this data is real, and it shows the bulb, but it also shows the shaft is sound with a good bottom echo. So it's kind of a complex result, but you can really, if you know what you're looking at, you can parse out quite a bit of information. Conversely, a shallow, narrow bulb just looks like a single upward break. It breaks up and breaks down, all in one single result. So this is a shallow bulb at about 24 feet. This is the second echo of a shallow bulb, because the bulb, you have it downward, upward, downward. And then the echo here is downward again. That tells us it's the bottom. So we know how deep our bottom is here. When you have a bottom bell or the situation of a shaft set into a hard rock, you get an upward break at the tip instead of a downward break. So this is what a bulb or a hard rock or a bell at the tip of a shaft would look like. This is a 57-foot shaft with a bell at the bottom. A neck, which is one of the things you're most commonly looking for, this is a partial neck where you have an echo going down again below the zero line and a second echo here. So you have 2 echoes from your neck at about 15 feet with a bottom echo at 47 feet. The presence of the bottom echo tells us that this neck is probably less than 50% of the shaft cross-sectional area. But it is difficult to get exact neck area reductions from SE data. This is a photo showing an actual shaft that was tested with SEIR and found a partial break in it. And this shaft actually had a problem when they were pulling the casing. The casing stuck and ripped the concrete. Some of the typical defect that you might find with sonic echo testing. All right, let's jump into the parallel seismic method. Again, for foundation tip depth, and sometimes, usually you can get foundation type if your data is clean enough. So we're looking at foundation depths, typically with superstructure on top. Again, as I noted earlier, it requires a borehole next to the foundation. Closer is better. The borehole needs to be at least 3 meters, 10 to 15 feet deeper than the expected foundation bottom if you want to see the tip of the foundation you're evaluating. What's nice about the parallel seismic method, though, is that it can be used to evaluate complex geometries underground. This is a buried pile cap with piles underneath it, an abutment with piles underneath it, or some sort of other, large pile cap where you have no access to the foundations themselves. It can also be used on steel sheet piles. It can be used on steel H piles, pretty much any type of deeper foundation. It's not as effective on shallow foundations, typically because the soil that doesn't carry sound waves very well from the foundation to the borehole. So effectively, you impact the top of your foundation, the sound wave travels through the foundation, and then couples over to your receiver in this water-filled borehole, typically a hydrophone. As you go down this foundation, it keeps coupling through. So as long as your foundation has a constant distance from your borehole, your travel time down and across is is a straight line. You have a linear increase in travel time. At a step like this, you'll have a little glitch in the data, followed by yet another linear increase. And below the tip, then the slope changes to now being the velocity from the soil. I'll show you some examples in a minute here. Quick overview of some of the equipment. You have a hydrophone on a spool, a large 12-pound sledge. An accelerometer is just used as a trigger in this case. You can also do the test with an instrumented hammer and a hydrophone, the instrumented hammer being your trigger. There's several different systems that can be used, but the basic requirements are some sort of signal analyzer data collection system, a hydrophone, although the test has also been done with downhole geophones. It tends to be much faster and more convenient with a hydrophone as long as you have water in the annulus and water in your borehole. Some sort of amplifier filter, an impact source, and you impact the superstructure. So here's some data, typical data from one single impact at one single depth. You impact here, it travels down the foundation through the soil and arrives at the hydrophone. Not much you can tell from a single waveform. So what we typically do after we collect the data at various parameters, typically 10 to 20 microseconds per point. These are some of the basic parameters used. Impact the structure. In this case, he's impacting the top of a pile cap. You can see these piles down here. By the way, the test in this case is going to be measuring the deepest pile. You're not going to be able, when hitting a pile cap, to differentiate one pile from the other. It's simply going to tell you which of these two piles is the deepest. And you can see our borehole is here. It's got a tape measure to measure the depth and a hydrophone cable going down. Another example, the borehole is actually kind of hidden out of sight, but you're impacting horizontally on the wall of a structure above the pile, and that also works quite well. So you collect the data. You can, if you've collected it in an NDE 360, you can export it, and eventually you run it into a program, in this case called IX Foundation, but you can use other programs that stack the data versus depth. And you can see the slope. So this is the slope of the foundation. The arrival time versus depth gives you the velocity of that foundation. Being 17,000 feet per second, that tells me this is a steel foundation, steel H-pile likely. Down here we have a different slope. This is from below your tip. And where these two lines intersect is your tip depth. So that's how the parallel seismic method works. This is a foundation that's about 18.6, 19 feet deep. These are some of the different. Okay. Some of the plotting parameters. You can plot different options with the IX foundation. But essentially, you're getting this depth, soil velocity, and pile velocity. Let me show a couple of case studies of parallel seismic. We'll start off with the levees in New Orleans. This was after Hurricane Katrina. This is a sheet pile wall, and used to be embedded in a levee. It has a short concrete wall on top. And the concern was in areas that were not washed out like this, how deep was this sheet pile? And were the sheet piles of adequate depth? This was quite a significant hurricane, as you probably are all well aware. You can see the devastation behind this failed levee. This is some of the some pictures just to show some of the devastation from Hurricane Katrina on New Orleans. Flooded homes, washed out roads, filled up, flooded out cars, etc. So this is that sheet pile wall, the concrete on top. The sheet piles are embedded into this concrete and go down into the levee. So again, you can see the top here. This is concrete. That's what you saw on those earlier slide. With steel sheet piles embedded into it, going down and into the levee as a cutoff. Here's Larry Olson impacting the wall above the sheet piles, and the borehole is some distance away. This is one example of doing the parallel seismic method. We tried doing it with the seismic cone penetrometer, and that actually also worked pretty well at this particular site. What I like about this slide is it does show quite well the cross section of this concrete wall with the sheet pile embedded going down into the soil. So the data from this was kind of unusual, or probably what we should have expected. We really didn't get much signal directly from the sheet pile or the concrete wall directly through the soil, through the levee material, because it's such loose fill and it's not saturated. But when we got down to the firmer materials, down to the pile tip, we got this, what I think of as a classic inversion here. And we have almost what we call an arrow pointing at the foundation tip. And so you have the soil material, the bedrock, as it were, 7,800 feet per second, pretty competent material below the fill material. And the sheet piles ending at about 21.8 feet. And the sheet piles tip out at the hard bedrock, which is what was desired. Another example, this is in Pearl Harbor area in Hawaii. Renovating a structure, they needed to know how deep the existing foundations were so they could tell if they could build additional structure on top of the foundation. Again, you have a pile cap with piles underneath. In this case, we were hitting the wall. In this case, we're hitting the pile cap. This is the data. The boreholes in this case went significantly deeper than the actual foundation tip. We have a velocity up here of about 12,000 feet per second. Velocity down here about 5,000, 5,100 feet per second. Lo and behold, 5,100 is about the speed of water. This is saturated material below the foundation tip, probably saturated old corals. Up here, 12,000 feet per second, that's the velocity of concrete. So this is a concrete foundation, which we already knew, leading into a saturated material with a tip depth of about 64 feet. We've got a few other examples. Again, this is a steel pile showing a tip depth of 24, 16,000 feet per second. 16 to 17,000 is typical of steel. When you get down to 12 or 13, that's going to be typical of concrete. Timber can be all over the place. Timber piles are a little harder. We've seen timber piles from 10,000 all the way up to 15,000 feet per second. This is a very short pile, again, showing just a little bit of data, but again, 12,000 feet per second, it's concrete. And we have loose or not so competent soil deeper down. Let's talk about some of the other three test methods. These are a little less common than the first two, primarily used for shallow foundations, impact echo and GPR, but we'll start with impact echo. Used again for footer evaluation and foundation mapping under slabs. So the impact echo is somewhat similar to the sonic echo test method. You impact the top of a slab, it bounces off a defect or the bottom of the slab and comes back up to the top. And you're measuring the depth of the bottom of the slab, similar to the sonic echo method. However, because it's so short, the echoes in time domain are very difficult to pick out. So we run it through a fast Fourier transform, and in the frequency domain, the impact echo method produces a single nice clear resonant frequency peak that corresponds to the depth of of the slab or the feature that you're measuring. The depth is equal to a beta factor, which is essentially near 1, times the velocity divided by 2 times that frequency peak. Similar equation to the impulse response method if you were listening earlier. So we use this to evaluate abutments, piers, pile caps. How thick is your pile cap? We've used it to locate piles underneath pile caps because you can locate areas where there is not an echo from the bottom of your pile cap. We've used it to test for thickness and integrity in hidden pile locations and looking for footers. One advantage of it, again, you only need access to one side. There is an ASTM standard, but it's really primarily for thickness determination, not for forensic applications. ACI 228 is probably a better reference for impact echo for forensic applications. Some of the equipment, this is a basic impact echo test head. We have our CTG2 system it's an integrated test head, battery powered, that runs right into a tablet and collects impact echo data. For very deep testing, like say a mat foundation that's on the order of 6 to 10 feet deep, we can use an accelerometer and do the impact echo. At some point, it sort of starts crossing over with the sonic echo method, but it's just a little different way of analyzing the very similar data. There's the impact echo data collected with our CTG2 thickness gauge, and you can even see the thickness peak here. Now, for foundations, we found it very useful to use a rolling scanner system for impact echo. This is our impact echo scanner system on the Data PC or the ND360, and it rolls across the top of a slab or footer, and every inch takes an impact echo test. So when you roll it down, here's what data might look like. This is some actual data from rolling across a slab at a house, I believe. So we have the time domain data here. We have frequency domain showing a peak at 7 inches. This is up where this cursor is. So it's a 7-inch slab rolling along. From 0 to 5 feet, it's about a 5-inch slab. Then there's a footer under the slab, 20-inch deep. Then after that, the slab is now 7 inches deep. So you can get quite a bit of information from one scan, which only takes a minute or two to collect. Let's jump over to the ground penetrating radar method, the GPR method. Typically can be used for a lot of different applications, but in this particular presentation, I'm going to discuss how we use it for shallow foundation evaluation. Most commonly for foundations, you're using a lower frequency antenna. 400 megahertz is one common common antenna frequency. Used to locate foundations under slabs or soil, or even under soil to find out, say, dead men foundations. You can also measure foundation location, top depth, and even the footprint. What is the cross-sectional area of your foundation? So this is a similar application to the impact echo method in that we're looking for footers under a slab. And this one, you can see the two footers here, or the footer range. This is an interesting application. This was a building in the basement of a large, older building they wanted to repurpose. And so without cutting through the slab, they wanted to know what's going on with foundations next to or underneath these various columns that went through the slab. So we used a 400 megahertz antenna wheeling across the floor with a distance wheel and collected long scan lines past a whole bunch of these columns all in the same scan. This is a part of one scan, and you can see that at about 2 feet deep, 24 inches, there's a reflector showing the top of the footer. Then at around 4 feet deep, there's a footer bottom. The footer length is evident here from the top scale. And this particular one was nice. They actually then went in and saw cut down to verify this. And sure enough, it was about 2 feet deep, and the dimensions matched up really well with the GPR data for this buried footer. Another example of scanning under a slab, this is scanning through a doorway in a house. And again, you can see that, yep, indeed, there is a footer underneath that door. Final application is kind of an unusual one. This is scanning horizontally on a buried basement wall looking for pier type foundations. So we scanned along this basement wall to see what's going on under this larger wall outside. And you can see, scanning horizontally, we can see these large foundations. There's 2 rows of piles, and they're both evident from scanning horizontally. So it's an example of using GPR to locate and verify the presence of foundations. The last method I'll touch on is the borehole electromagnetic foundation rebar evaluation. Typically, we've used it to locate the presence or absence of steel near the borehole, most commonly for looking for rebar. But it can also be used to locate or measure the depth of steel H-piles. The biggest limitation of this method, you have to get your borehole really close to the steel that you're trying to measure. If it's more than 2 feet away, it probably won't work, or it won't work very reliably. But if you can get it right up against the foundation, it works really, really well. So here's me. Then this is the borehole tool, and we lowered it into this PVC pipe. If you look carefully, you can see the client has chipped out in this wall a column. This column is connected to the foundation that we're interested in verifying the rebar depth on. We got this data, and you can see the bottom of at the expected tip depth of the foundation, around 21 feet. We get a beautiful, huge glitch in the EM data, which verified that, yep, there's the rebar mat. It ended right here, and it worked quite well. So I'd like to thank you for listening to my presentation on foundations. At this point, we're going to open it up for questions. Please type them into the chat bar, and Ryan will let me know what they are. We'll take a look, and we'll see if we can, how many of these questions we can answer. Thank you.
All right, so I'm going to start at the top of the question list. The first one is, can GPR or Impact Echo identify the rebar size in foundations?
No, the GPR can sort of measure rebar size, but it's really not the ideal tool for GPR. The best way to measure rebar size is frankly with one of the many rebar locators that are out there that can measure the rebar diameter right at the top. The way we've measured rebar diameter with GPR is frankly by measuring the top depth of 2 mats that are perpendicular to each other and assuming that the 2 mats are tied to each other. You measure the difference and you can get the approximate bar diameter. The acoustic methods are not useful at all for GPR, for rebar. In fact, we consider that one of the strengths of the acoustic method in that they essentially blow right past the rebar. You're measuring the concrete itself, not the rebar. Do you have another question?
Yep. So this is not a question that's technical, but
okay.
Just confirm to everyone that we will be posting the video.
Yes, we will be posting this, a copy of this video online. It might take a few days. Our editor is currently in London, but she will still be working on it. And we'll get this video up there, and we'll actually be, I believe, sending an email link out to everybody who registered. So you'll have an email showing with a link to this video. And we're happy to have you copy it, download it, play it to whoever you'd like.
All right. The next question is, at what distance can a wave be considered a plane wave?
Okay, in a drilled shaft, my understanding is that it takes about 2 diameters for the impact, particularly if you're impacting towards the side of a drilled shaft, to become a true planar wave all the way across the shaft diameter. So if you have a 3-foot diameter shaft, it usually takes about 6 feet of depth before it's a plane wave. And the importance of a plane wave, if you're wondering, is that once it's a plane wave, it really is going to be seeing a defect no matter where it is in the shaft diameter. It will echo from anything. On the other hand, you won't know where that echo is coming from. You'll just know that you have an echo at a certain depth. You'll know the depth, but not the location horizontally.
The next one is more of a comment.
Okay.
I'm sure that you can respond to it.
Okay.
We did a short H-pile impulse response test recently, and it was extremely difficult to record enough meaningful reflected energy.
Yeah, well, even with short H piles, it gets really difficult because the principle, I talked about the length to diameter ratio limitation on the echo test method. Well, the reason that there's a limitation on the length to diameter is that as your wave is traveling down the shaft, energy is going out into the soil. And if you have the energy itself is being carried down the shaft by the mass of the pile. An H pile is almost all surface area. So much more energy dissipates into the soil compared to, say, a round drilled shaft or a square concrete pile or a timber pile for that matter. So a timber pile or a concrete shaft can carry the energy down the shaft and lose a lower percentage of its energy per foot of depth into the soil compared to an H pile. The H pile energy just dissipates really fast out of the sides of the H pile. And remember, you've got it with an echo test, you've got to go down to the tip of the H pile and then back up again. So you're losing more energy as you go back up. Parallel seismic, it only has to measure the energy going down, and then that couples into the soil, through the soil to the hydrophone. And we can raise the gain on that hydrophone very high because there's no other sources of energy. With an echo test, when you hit the top of your pile, you're generating a pretty good amount of energy that echoes around in the top and can mask really, really weak echoes. And so in general, I wouldn't use echo testing on an H pile. That's the overall conclusion. Another one?
Can the SE method be used to evaluate deep soil mixing columns?
That's an interesting question. We've experimented a little with that. And in general, I would say no, because most of the time when we've run into soil mixing, it is not even enough. And too much of the energy is dissipated on all these little interfaces. And it's not concrete-like enough. If it's very, very concrete-like and has a relatively constant diameter, you might get an echo, but it's really difficult. We've also experimented, just as an aside, on using cross borehole tomography on soil mixing, and that can work if you have a larger area. And SASW, and there's some geophysical tools that probably Ryan can comment on in a different context. But so evaluating soil mixing is probably a seminar in and of itself.
All right, the next one is, with a steel column in place on a foundation, how do you separate the response from upward traveling waves from downward traveling waves?
Yeah, that can be interesting. Normally, the steel column won't carry the wave energy, depending on the nature of the steel column. If it's a hollow column, it really won't carry much at all. Or if it's a steel like I-beam, it won't carry too much energy. You're hitting the concrete, you're impacting the concrete, your receiver is mounted on the concrete. We get some ringing from the column, but generally we can differentiate that pretty easily. If you're worried about it, what I would do is measure the height of the steel column so that knowing the velocity of sound through steel, you can then determine where an echo from the top would come from, so you can ignore that particular echo if it does show up in your data. The other thing we've done is mount a second accelerometer on the steel column to measure the upward going wave. If you mount it partway up the column, you'll see how strong a wave is going up that column and whether the energy is significant. You'll also be able to then differentiate that from the energy going down. Hopefully that answers the question there.
Okay, the next one's sort of a comment.
Yeah.
But it said that someone said that when they were making measurements and looking to use polarity for interpretation,
yeah,
that they were plugging into their headphone jack on their computer.
Yeah.
And sometimes it reversed polarity.
Oh, right. Well, what's important, for differentiating between a bulb and a neck, for instance, you're looking at the reversing polarity. What's important is that the polarities reverse. One goes up, one goes down. You can have an upward going break at the start. You would expect your bottom to, if it's a neck, to be another upward going break. If you have an upward at the top, you would expect the bulb to be down. If you have a downward at the beginning, you'd expect the bulb to go up. So it's just a matter of how you look at it. And frankly, there's some of the tools out there, some other systems use upward breaking records for analysis. I happen to be used to downward breaking, so I tend to invert them. But there are, it's not a particular problem, it just looks different.
Okay. With wave speeds being estimated, is it reasonable to estimate pile length to 1/10 of a foot?
No, I would never try to measure pile length to 1/10 of a foot. Typically, we tell people about 10%. Because the waves, first of all, the wave speed is being estimated. The second of all, if you looked at some of those echoes, those waveforms that I was showing in the examples, the frequencies we're using to get down to the bottom of the pile and the curvature, results in curvature of those waves, that's pretty rounded. So picking the peak gives you enough slop that 1/2 a foot is a really, really tiny amount. I could probably move it up and down by easily 1/2 a foot and still have it mostly on the bottom of that echo. Typically, again, 10% is what we specify. Now, in shallower foundations, we use smaller hammers that generate higher frequencies, and you can pick to a tighter depth range. And so in that case, 1/2 a foot might be reasonable if your shaft is only 10 feet long. But if you're testing a 50-foot shaft, we typically specify 10% just to allow for other variations. You can get down to 4 or 5% if you measure the velocity of the concrete in the shaft.
All right, the follow on was, what's the effect of heavier hammers?
Well, heavier hammers, there's kind of there's two different ways of looking at that. There's heavy hammers and there's different tips. So heavy hammers generate more low frequency energy. Also, softer tips generate lower frequency energy. The hammers that we use have replaceable tips. The black tip is considered the hardest one, other than an actual metal tip, followed by the red tip, green, brown, etc. And the softer tips or larger hammers generate more energy, and in theory, you can see down deeper down a large shaft. Typically, we'll use a softer tip like a red tip on a shaft that's more than 70 to 80 feet long. And it gives us a little better tip depth echo information compared to, say, a black tip. On the other hand, if a shaft is only 10 feet deep, or you want to see clearly a defect that's showing up at very shallow depths, you're better off retesting or testing initially with a smaller hammer. We have 1-pound instrumented hammers. We use ball peen hammers on very short foundations. Very commonly on, say, light pole foundations that might only be 5 to 8 feet deep, you would test those with a 1/2-pound ball peen hammer. And so, yeah, there is a relationship between hammer size and how deep you can test a foundation. But there's quite a bit of overlap as well.
If the top of your foundation is underwater, for example, a stream bed, is it possible to use the parallel seismic bed?
Oh, yeah, absolutely. If you can get the borehole in, which shouldn't be a problem, what we have done in that case is you can take a steel rod, put it down to the top of the pile, and hit the top of the steel rod. You just need to be able to introduce energy into the foundation that has a constant start time. In other words, you have to use the same rod length and hit the same location and have the rod at the same location in your foundation. And that actually can work quite well. So, and there's variations on that. It doesn't have to be a steel rod. You can put a chunk of concrete on top of your foundation and hit that. But we've had the best luck just impacting something, a steel rod with an instrumented hammer. Or you can mount a small accelerometer to the side of your steel rod with a magnet and use that as your trigger. So there's a couple of different options. But yes, you can definitely measure a foundation with the top underwater.
Can you tell if a pile shaft is vertical versus battered if you know the verticality of the borehole?
With parallel seismic, you can try to parse that out, but you'd have to know what kind of foundation it is as well, because your battering of your pile will give you an artificial it'll affect your apparent velocity. So it will increase or decrease the apparent velocity because it will decrease or increase the slope, the arrival time versus depth slope. If you know the velocity of the pile, for instance, if you know it's concrete, you could parse out using some math the approximate batter of the pile, again, assuming your borehole is exactly vertical. I don't know if we've ever tried to do that. We've had couple of cases where we've certainly seen battered piles, but usually they're not haven't been worried about what the angle is. But I think you could do that if you have clean data and you know what kind of pile you have.
What is the best way to calibrate shallow rebar cover with GPR?
Maybe you can answer that one, Ryan.
I assume they're just asking, how do you estimate
Yeah.
depth?
Frankly, the best way is to actually chip down, drill down, et cetera, to a known rebar depth and do a GPR scan right across the top of that location. Because the concrete can have different dielectric constants, different velocities, and so to calibrate a rebar depth in a given slab, this is kind of outside the area of foundation evaluation, but typically the best way is to actually chip down to a known rebar depth in your actual slab.
Is GPR dependent on soil type?
Absolutely, yeah. The penetration depth, the usability of GPR in some soil types, like here in Denver, if you have wet clays, you won't get more than a few feet of penetration depth. On the other hand, if you have dry, sandy soils, you might see a foundation that's 20 feet deep, 20 feet down to the top of it. So GPR is very dependent on soil type.
So this one is, how can you repair breaks or cracks once you've identified them?
Oh, it gets kind of interesting. If it's shallow enough, we've seen cases where people have excavated down the side of a shaft, like that example I showed, that one photo I showed of a ripped shaft, and chipped out the bad material and actually reformed and packed and placed concrete in to repair it. There are some people have attempted to repair shafts using drilling and injection. That is very difficult. In our experience, it rarely works. We had one unusual situation here in Denver where there was a large diameter drilled shaft with a defect that was actually located with cross-hole sonic logging, but it was still a defect. They drilled a 3-foot diameter hole down the middle of the shaft and lowered a person in there, and he finished chipping it out, and then they refilled it with concrete, and that worked. But that's an extreme example. In our experience, it's often very difficult to repair a shaft that has a defect, particularly if the defect is too deep to excavate down to from the outside.
Okay. Can you comment on the reliability of methods, the importance of using multiple methods, as well as managing expectations of the client?
Yeah, managing expectations is very important. We firmly believe in that up front. That's one of the things I was hopefully trying to communicate today, is what the limitations of each method are. And that's very important to communicate to clients. Is the methods have strengths, but each method has a limitation, and you don't want to overpromise what it can do. If you have an opportunity to do two methods, we have very often tried to do echo testing and parallel seismic, but usually the reason we're doing one method or the other is because the other method isn't available to us. For instance, if there's no borehole, you can't do parallel seismic. If there's no access to the foundation itself, you can't do an echo test, or if it's a steel H-pile. But we have had occasions when we've had a borehole to do parallel seismic, plus we've had some sort of access to the foundation top or side, and we've done both methods. And that sometimes can give you what I might call warm fuzzies. You can get a little more verification of the methods. Anytime you can compare the results to drawings, to known information, that's also helpful. Or to boring information that might tell you where bedrock is. For instance, if you're doing parallel seismic and the results show that your foundation tips at 40 feet, and the boring information from putting the borehole in shows that bedrock was at 35 feet, that would make a lot of sense, that the foundation went into the bedrock a short distance.
The thickness of a concrete foundation on top of rock be measured using the pulse echo technique or something similar to the Mira instrument.
Okay, the Mira instrument, by the way, uses shearing. It's a pulse echo. All of the acoustic methods depend on changes in acoustic impedance to measure the depth to the various interfaces. So you're looking for echoes, whether it's a Mira pulse echo or an impact echo or a sonic echo. The problem you run into at a concrete to rock interface is that some rock can be very concrete-like. If your rock has a similar acoustic impedance to the concrete, and the concrete is well bonded to the rock, you can imagine the wave that you generate will just keep going down into the rock and you won't see any echo at all. However, if your rock is harder than the concrete, which is not uncommon, or your rock is somewhat softer than the concrete, which is probably even more common, you will see an echo, albeit it might be somewhat weaker than you'd get at a rock to, say, or concrete to soil interface. But there are situations, certain circumstances, where the acoustic impedances match so well that there just is no echo. And that has happened. It's not very common, but it does happen.
Have you used the impact echo method to measure asphalt thickness?
We have. I've successfully used it. There's a couple of limitations. First of all, a lot of asphalts are laid up in layers. They're added to over the years, or even when they're initially placed, they're placed in layers. And those layers aren't always well bonded to each other. So the impact echo can't see through an unbonded layer or a poorly bonded layer. The other limitation is impact echo doesn't work well in asphalt when it's hot. When it's hot, the top of the asphalt is really soft, and you can't generate a very high frequency impact when you're hitting something that's soft and mushy. So we prefer a test technique called spectral analysis of surface waves to measure asphalt. It measures asphalt velocity, measures asphalt depth, etc. Again, that's a different presentation, but another application, a different method.
There's a question about PDH credits.
We are not approved in New York. My understanding, we don't give out a certificate. Do we? You can certainly submit this. Many states will certainly accept this, but we don't have a certificate that we're sending out.